This cosmic ray climate link is controversial. Some studies support it. Others find no correlation. The effect, if it exists, is probably small, certainly smaller than the effect of greenhouse gases or orbital variations. But during a period of rapid change, even small forcings can tip the system from one state to another. There is also a more speculative connection. Some researchers have proposed that magnetic field changes could affect the stability of ice sheets through electrical effects on the ionosphere and atmosphere. Others have suggested that large-scale geomagnetic shifts might trigger volcanic eruptions by changing stresses in the crust. These ideas remain at the fringe of mainstream science. They lack strong supporting evidence, but they illustrate the range of possibilities that researchers have considered. The honest assessment is that we do not know whether magnetic events contributed to the Younger Dryas. The freshwater hypothesis remains the best supported explanation. The impact hypothesis has largely failed to withstand scrutiny. Magnetic connections are speculative, but the Younger Dryas demonstrates something important. Earth's climate can change rapidly, within years, within decades, faster than human societies can adapt. The current warm period is not guaranteed. The stability we take for granted is conditional. The megafloods of the Younger Dryas were real. The geological evidence is written across North America, the channeled scablands of Washington state, the giant ripple marks visible from satellites, the erratic boulders deposited hundreds of kilometers from their source. These features record floods of staggering magnitude, waters moving faster than any modern river, carving canyons in days that would take millions of years to form under normal conditions. For decades, the geologist who first proposed that floods had carved these features was ridiculed. J. Harlan Brett spent his career documenting the evidence, facing dismissal from colleagues who considered catastrophic flooding an impossibility. Gradualism was the ruling paradigm. Rivers erode slowly. Canyons form over eons. The idea that a single flood could reshape a landscape was considered heresy. Brett's was eventually vindicated. The evidence was too strong to ignore. Today, the megafloods are accepted scientific fact. The mechanism, the failure of ice dams containing glacial lakes, is understood. Catastrophism, in this limited sense, has been rehabilitated. But some have taken the lesson too far. They see catastrophes everywhere. They claim that pole shifts, magnetic or crustal, have repeatedly devastated civilization. They argue that advanced cultures existed before the last ice age and were destroyed by sudden cataclysms. They cite ancient maps that supposedly show ice-free Antarctica, myths from around the world that describe floods and fire from the sky, structures that seem too sophisticated for the cultures attributed to them. These ideas have captured public imagination. Books about lost civilizations sell millions of copies. Documentaries attract millions of viewers. The internet amplifies every claim, every speculation, every departure from mainstream science. In the next chapter, we will examine these catastrophist theories. We will consider the work of Charles Hapgood, the historian who proposed that Earth's crust periodically shifts over the mantle. We will look at the popularizers who have built on his ideas, and we will assess what is credible and what is not. Stop, waiting for confirmation to continue with chapters 6 through 10. Chapter 6, The Catastrophists, 1958. A professor of history at a small college in New Hampshire publishes a book that will haunt geology for decades. Charles Hapgood is not a geologist. He is not a physicist. He is not trained in any of the sciences that might qualify him to make pronouncements about how the Earth works. But he has an idea so radical, so sweeping, that it captures the imagination of readers who feel that mainstream science has become too cautious, too incremental, too boring. The book is called The Earth's Shifting Crust. Its central claim is extraordinary. Hapgood argues that the entire outer shell of the Earth, the crust that carries continents and ocean floors, periodically slips over the underlying mantle, not the slow drift of plate tectonics, not centimeters per year over millions of years, rapid catastrophic displacement, thousands of kilometers in perhaps a few thousand years, perhaps much faster. The mechanism Hapgood proposes is ice. During ice ages, massive glaciers accumulate at the poles, but not symmetrically. The weight is distributed unevenly. This imbalance, Hapgood argues, creates centrifugal stress as the Earth rotates. Eventually, the stress becomes too great. The crust breaks free from whatever anchors it to the mantle and slides to a new position. Regions that were polar become temperate. Regions that were temperate become polar. The climate changes overnight. Civilizations are destroyed. The book carries a foreword by Albert Einstein. This fact has been cited endlessly by Hapgood's supporters as evidence that his ideas have scientific merit. Einstein, after all, was the greatest physicist of the 20th century. If he endorsed Hapgood, surely the theory deserves serious consideration. The reality is more nuanced. Einstein was intrigued by Hapgood's hypothesis, but expressed reservations. He doubted that the weight of polar ice was sufficient to overcome the friction anchoring the crust to the mantle. He encouraged Hapgood to investigate further, but did not endorse the theory as proven. Einstein died in 1955 before the book was published. He never saw the final version or the interpretations that would be built upon it. The scientific community was not persuaded. By the 1960s, the theory of plate tectonics was emerging as the new paradigm for understanding how the Earth works. Continental drift, once dismissed, was being validated by evidence from the ocean floors, but plate tectonics operates slowly. Continents move a few centimeters per year. Mountain ranges build over millions of years. The catastrophic displacement Hapgood proposed was incompatible with everything geologists were learning about how the planet actually behaves. Moreover, the mechanism did not work. Calculations showed that polar ice, even at its maximum extent during ice ages, did not exert enough force to displace the crust against the friction of the mantle. The crust is not floating freely. It is coupled to the mantle beneath. Breaking that coupling would require forces far greater than ice accumulation could provide. Hapgood modified his theory in later works. He moved away from ice as the trigger and proposed that unknown forces within the mantle might cause displacement. He invoked the 1963 discovery that the mantle contains a partially molten layer, the asthenosphere, which might serve as a lubricating surface. But he never provided a satisfactory mechanism. The theory remained a hypothesis without a plausible physical basis. What Hapgood did provide was a story, a narrative of lost civilizations, of ancient maps showing coastlines that modern explorers had not yet charted, of sudden catastrophes that wiped away entire cultures and left only tantalizing traces for later generations to puzzle over. In Maps of the Ancient Sea Kings, published in 1966, Hapgood examined historical maps that he claimed showed geographical knowledge impossible for their era. The most famous was the Piri Reis map, drawn by an Ottoman admiral in 1513. The map depicts the Atlantic Ocean with reasonable accuracy. Its southern portion shows a coastline that Hapgood interpreted as the northern coast of Antarctica, ice-free and accurately charted. If true, this would be remarkable. Antarctica was not officially discovered until 1820. Its coastline under the ice was not mapped until the 20th century. How could a 16th century Ottoman admiral have access to accurate charts of a continent buried under kilometers of ice? Hapgood's answer was that the Piri Reis map was based on much older source maps created by an advanced maritime civilization that existed before the last ice age. This civilization charted the world when Antarctica was temperate, before crustal displacement moved it to its current polar position. The knowledge was preserved, copied, transmitted through generations until it reached Piri Reis, who incorporated it into his own work without understanding its origins. The interpretation has been thoroughly critiqued. Scholars of cartography have shown that the supposed Antarctic coastline is actually a distorted representation of the South American coast, bent to fit the parchment available to the mapmaker. The accuracy of the map varies wildly. Some coastlines are reasonably correct, Others are wildly inaccurate. The map shows features that do not exist and omits features that do. It is exactly what we would expect from a 16th century map based on incomplete and sometimes erroneous source material. But the Piri Reis map has become a touchstone for alternative historians. It appears in countless books and documentaries. It is cited as proof that ancient civilizations possessed knowledge that has been lost. The debunkings are ignored or dismissed as mainstream science protecting its turf. Hapgood died in 1982, struck by a car at age 78. His theories had gained little traction in academic circles, but had found a devoted popular audience. In the 1990s, that audience expanded dramatically when a British journalist named Graham Hancock published Fingerprints of the Gods. Hancock took Hapgood's framework and expanded it. He argued that a sophisticated global civilization existed during the last ice age. This civilization possessed advanced knowledge of astronomy, mathematics, and engineering. It built structures whose remnants can still be seen, from the pyramids of Egypt to the megaliths of South America to the temples of Southeast Asia. When the Ice Age ended, catastrophic pole shifts, floods, and other cataclysms destroyed this civilization. Survivors scattered, carrying fragments of their knowledge to various parts of the world, seeding the historical civilizations that mainstream archaeology recognizes. The book was a bestseller. It spawned sequels, television series, speaking tours, and a cottage industry of alternative history. Hancock became one of the most influential popularizers of catastrophist ideas in the modern era. His claims have been systematically challenged by archaeologists, geologists, and historians. The structures he cites as evidence of an advanced Ice Age civilization have well-documented construction histories. The astronomical alignments he interprets as evidence of sophisticated ancient knowledge can be explained by much simpler hypotheses. The geological evidence he invokes for sudden catastrophes has alternative explanations that do not require lost civilizations. Yet the ideas persist. They resonate with audiences who distrust official narratives, who suspect that history is more mysterious than textbooks admit, who find mainstream explanations too mundane for phenomena that seem genuinely extraordinary. Is there any kernel of truth in these theories? The honest answer is complicated. There is no evidence for crustal displacement of the kind Hapgood proposed. The physics does not work. The geological record does not support it. The magnetic reversals we have discussed in this documentary are not the same as crustal shifts. They involve changes in the direction of the magnetic field, not the physical movement of continents. There is no evidence for an advanced Ice Age civilization. The archaeological record shows a clear progression from simple tools to complex societies. The earliest cities appear around 10,000 years ago. Large-scale agriculture begins around 12,000 years ago. There are no artifacts, no structures, no written records that predate this timeline and require explanation by lost civilizations. But there is evidence that the ancient past was more complex than we once thought. Sites like Göbekli Tepe in Turkey, built more than 11,000 years ago, show that hunter-gatherer societies were capable of monumental construction long before the advent of agriculture. The sophistication of Stone Age peoples has been repeatedly underestimated. This does not validate Hapgood or Hancock. It simply shows that human creativity and capability have deeper roots than earlier scholars recognized, and there is evidence that catastrophes have shaped human history. The Younger Dryas was real. The mega-floods were real. The end of the Ice Age was a time of dramatic environmental change. Coastlines shifted, habitats transformed. Some human populations thrived, others disappeared. These events left marks on collective memory. Flood myths appear in cultures around the world. They may reflect genuine experiences of rising seas, of rivers that overtopped their banks, of weather that became unpredictable and violent. The question is how to interpret this evidence. Catastrophists see confirmation of their grand theories. Mainstream scientists see natural processes operating through time. sometimes gradually, sometimes abruptly, but always following the laws of physics and leaving evidence that can be studied. The magnetic pole shifts we have discussed in this documentary are real. They are documented. They have consequences, but they are not the crustal displacements that Hapgood imagined. They are changes in the orientation of Earth's magnetic field, driven by processes in the liquid outer core. They do not move continents. They do not flip the planet on its axis. They do not relocate Antarctica from the tropics to the pole. What they do is weaken the shield that protects us from space, and that has implications for a technological civilization that the ancient world never faced. In the next chapter, we will return to hard science. We will examine the South Atlantic anomaly, the growing weak spot in Earth's magnetic field that is already causing problems for satellites and astronauts. We will see what the data shows about the current state of the shield, and we'll consider what might happen if the weakening continues. Chapter 7. The South Atlantic Anomaly. High above the South Atlantic Ocean, approximately 400 kilometers up, the International Space Station glides through the darkness. Astronauts aboard are going about their routines, experiments, maintenance, exercise to combat the bone loss that comes from living in microgravity. Then the station crosses an invisible boundary. Warning lights flash. Sensitive equipment powers down automatically. The crew has been briefed on this. They know what to expect. Some report seeing flashes of light even with their eyes closed, cosmic ray visual phenomena, high-energy particles passing through their eyeballs and triggering the retina, shooting stars inside their skulls. The station is passing through the South Atlantic anomaly, a region where Earth's magnetic field dips to its lowest values, a zone where the Van Allen radiation belts, those donut-shaped regions of trapped charged particles that normally orbit high above the atmosphere, come closest to the surface. Close enough to threaten electronics, close enough to dose humans with radiation levels significantly higher than elsewhere in low Earth orbit. The anomaly was first identified in the 1950s, early in the space age. Scientists mapping the radiation environment around Earth discovered that the belts were not symmetric. On one side of the planet they stayed comfortably high, on the other they sagged downward. Over South America and the adjacent Atlantic, the inner radiation belt dipped to altitudes as low as 200 kilometers, well within the orbital range of satellites and crewed spacecraft. The cause is the geometry of Earth's magnetic field. The field is not centered on the planet's core, it is offset, tilted. The magnetic axis does not align with the rotational axis. If you imagine the field as produced by a giant bar magnet buried inside the Earth, that magnet would not sit at the center. It would be shifted toward the Western Pacific. This displacement means the field is weaker on the opposite side of the planet. Over the South Atlantic, the effect is significant. Field strength in the anomaly is roughly 3 times weaker than at comparable latitudes elsewhere on the globe. The Van Allen belts respond to this weakness by dipping lower. Charged particles that would otherwise be trapped high above the atmosphere spiral downward, following the weakened field lines until they reach altitudes where satellites operate. The practical consequences have been documented for decades. Satellites passing through the anomaly report higher rates of single-event upsets. Bit flips in computer memory caused by energetic particles striking silicon chips. Most of these upsets are harmless. The software catches the error and corrects it. But some cause glitches, instrument malfunctions, data corruption, occasionally catastrophic failures. The Hubble Space Telescope routinely shuts down its most sensitive instruments when passing through the anomaly. The risk of damage is too high. Better to lose a few minutes of observation than to lose the detector entirely. Astronauts on the International Space Station receive more than half their total radiation dose while passing through the anomaly, despite spending only a small fraction of their orbital time there. Long-duration missions must account for this exposure. Career limits on radiation dose constrain how long astronauts can serve in space. The global star satellite network experienced a wave of failures in 2007, attributed to radiation damage accumulated during repeated passages through the anomaly. Other satellite operators have reported similar problems. The region is a hazard that must be designed around, shielded against, or simply endured. But here is the concerning part. The anomaly is growing. Data from the European Space Agency's Swarm satellite constellation, which has been mapping the magnetic field since 2013, shows that the South Atlantic anomaly has expanded significantly over the past decade. Between 2014 and 2025, the area of weakest field grew by nearly 2 million square kilometers, an area almost half the size of continental Europe added in just 11 years. Moreover, the rate of weakening has accelerated. Since 2020, the expansion has intensified. Different parts of the anomaly are changing at different rates. The region approaching Africa is weakening faster than the region near South America. Something is happening deep in the outer core that is reshaping the field in this area more rapidly than expected. Chris Finlay, a geomagnetism researcher at the Technical University of Denmark who led the analysis of the swarm data, described the findings in measured but sobering terms. The South Atlantic anomaly is not just a single block, he noted. It is changing differently towards Africa than it is near South America. There is something special happening in this region that is causing the field to weaken in a more intense way. What is that something? The current hypothesis involves reverse flux patches, regions at the core mantle boundary where the magnetic field points in the opposite direction from the main dipole. Normally, field lines emerge from the core in the southern hemisphere and re-enter in the northern hemisphere. But beneath the South Atlantic anomaly, patches exist where the field does the opposite. It goes back into the core rather than emerging from it. These reverse flux patches effectively cancel out part of the main field. Where they exist, the surface field is weaker. As the patches grow or move, the anomaly expands. The patches appear to be connected to structures deep in the mantle. The African Large Low Shear Velocity Province, a vast dense region beneath Africa and the South Atlantic, may be influencing how heat flows out of the core and how convection patterns develop in the liquid iron. This connection between deep Earth structure and surface magnetic phenomena is an active area of research. The question on everyone's mind is whether the South Atlantic anomaly is a precursor to something larger. Is it the first sign of an impending reversal, a region where the field is rehearsing its collapse before the rest of the planet follows? Scientists are cautious about drawing this conclusion. The paleomagnetic record shows that the field has weakened many times in the past without reversing. Anomalies have appeared and disappeared. The current weakness could be a temporary fluctuation, a local phenomenon that will stabilize or even reverse in the coming decades. But the possibility cannot be dismissed. Reversals do not happen uniformly across the planet. They begin somewhere. Patches of reversed polarity appear and grow. The dipole weakens, multiple poles emerge. The field becomes chaotic. Then, eventually, a new dipole establishes itself with the opposite orientation. The South Atlantic anomaly has the characteristics of such a beginning. Reversed flux patches, growing weakness, accelerating change. It is exactly what you would expect to see in the early stages of a reversal. Or it could be nothing, a fluctuation that will fade. The Earth's way of breathing magnetically, expanding and contracting, without ever fully inhaling or exhaling. The data does not yet distinguish between these possibilities. We are watching something happen. We do not know what it means. What we do know is that the practical consequences of the anomaly are already being felt. Satellites are affected. Astronauts are exposed. The region of elevated radiation risk is growing. Even if the anomaly never triggers a reversal, even if the field stabilizes tomorrow, the damage it causes is real and increasing. The Swarm mission has also revealed other changes. The magnetic field over Siberia is strengthening. The field over Canada is weakening. The North Magnetic Pole, as we discussed earlier, is racing from Canada towards Siberia. These changes are connected. They reflect the same underlying reorganization of the outer core that is expanding the South Atlantic anomaly. The picture that emerges is of a magnetic field in flux, not catastrophically collapsing, not imminently reversing, but changing, evolving, responding to processes deep below that we can observe but not fully explain. The next decade of satellite observations will be crucial. If the anomaly continues to expand at its current rate, if the weakening accelerates further, the case for an impending reversal will strengthen. If the expansion slows or reverses, we will have dodged a bullet we did not fully understand. In the meantime, engineers design satellites to withstand higher radiation doses. Astronauts accept the risks of their profession. Airlines routing flights over the South Atlantic factor in slightly elevated cosmic ray exposure. The world adapts, as it always does, to the hazards that cannot be eliminated. But adaptation has limits. If the field weakens globally, if what is happening over the South Atlantic spreads to other regions, the challenges will multiply. Power grids, communication networks, navigation systems. The infrastructure of modern civilization was built assuming a magnetic field of approximately current strength. No one designed for a world where the shield is half as strong or 1/10 as strong. In the next chapter, we will look deeper still, past the mantle, past the outer core, into the very center of the planet where recent discoveries suggest that even the solid inner core is behaving in unexpected ways. The heartbeat of Earth's magnetism may be changing its rhythm. Chapter 8. Earth's core in motion. 3,000 kilometers beneath your feet, deeper than any drill has ever reached. Deeper than any human will ever go, sits a ball of metal roughly the size of the moon. The inner core. Solid iron and nickel compressed under pressures millions of times greater than the atmosphere at sea level, heated to temperatures approaching 6,000 degrees Celsius. Hot enough to melt steel at the surface, but solid down there because pressure forces the atoms into rigid crystalline structures despite the heat. The inner core is the seed around which the planet formed. The densest material, the heaviest elements sank toward the center as Earth coalesced from the solar nebula 4.5 billion years ago. It has been growing ever since. As the outer core cools, iron crystallizes at the boundary between liquid and solid, adding to the inner core layer by layer. The growth is slow, perhaps a millimeter per year, but over billions of years, the core has reached a radius of approximately 1,220 kilometers. For most of the history of seismology, the inner core was simply there, a solid obstacle that seismic waves had to pass through or around. Scientists could measure its size, estimate its density, infer its composition, but it was static, unchanging, a fixed feature of Earth's architecture. Then, in 1996, everything changed. Two geophysicists at Columbia University, Xiaodong Song and Paul Richards, published a paper in Nature that proposed something extraordinary. The inner core, they argued, was rotating, not at the same speed as the rest of the planet, faster. The solid metal ball at the center of Earth was spinning slightly faster than the mantle and crust above, completing an extra rotation roughly every 400 years. The evidence came from seismic waves. Earthquakes generate waves that travel through the entire planet. Some pass through the inner core. By comparing the travel times of these waves over decades, Song and Richards detected subtle changes. The path through the core that waves took in the 1960s were not quite the same as the paths they took in the 1990s. The difference was consistent with a core that had rotated relative to the surface. The finding was controversial. Other researchers reanalyzed the data and got different results. Some confirmed the rotation, but at different speeds. Some found no rotation at all. Some proposed that the core was oscillating back and forth, rather than continuously spinning in one direction. The debate consumed seismology for years. By the early 2000s, a rough consensus emerged. The inner core does rotate independently of the mantle, but the speed is uncertain. Estimates ranged from 1 degree of extra rotation per year to less than 1/10 of a degree. The mechanism was also unclear. The inner core is surrounded by liquid. It is not mechanically coupled to the mantle, but it is magnetically coupled. The magnetic field generated in the outer core interacts with the solid inner core, pushing and pulling it. Gravitational interactions with dense structures in the mantle also play a role. The balance of these forces determines how fast the core spins. Then came 2023. A new study, again led by Xiaodong Song, now at Peking University, made headlines around the world. Analyzing seismic data from repeating earthquakes that occur in the same location years apart and generate nearly identical signals, Song and his colleague Yi Yang found something unexpected. The inner core appeared to have stopped. After decades of super rotation, spinning faster than the surface, the core had slowed. By around 2008 or 2010, it had matched the rotation speed of the mantle, and then it had begun moving backward relative to the surface, sub-rotating, spinning slower than the planet above it. The media coverage was predictably sensational. Headlines declared that Earth's core had stopped spinning. Some suggested apocalyptic consequences. Social media amplified the alarm. The reality, as usual, was more nuanced. The core had not stopped rotating in any absolute sense. It was still spinning in the same direction as the rest of the planet. It had simply slowed relative to the mantle. If you stood on the surface and watched the core, it would appear to be drifting backward, a retrograde motion produced by the difference in rotation speeds. Song and Yang proposed that this change was part of a cycle. Their data suggested that the core oscillates between periods of superrotation and subrotation over roughly 70 years. In the 1970s, the core was spinning faster. By the 2000s, it had slowed and begun moving backward. In coming decades, it would presumably speed up again. The hypothesis was elegant but not universally accepted. Other researchers cautioned that the seismic data was ambiguous. The signals being interpreted as rotation changes might have other explanations. Variations in the structure of the inner core itself, changes in the properties of the outer core that affect wave propagation. The debate was far from settled. In 2024, new studies provided additional support for the slowdown. John Vidal at the University of Southern California analyzed seismic data from nuclear tests conducted in the 1970s and earthquakes recorded in the decades since. His team found clear evidence that the inner core's rotation had changed. The patterns were consistent with a slowdown beginning around 2010. More intriguingly, Vidal's team found hints that the inner core might not only be rotating differently, but also changing shape. Subtle variations in seismic wave patterns suggested that the surface of the core was not static. Features were shifting. The boundary between solid and liquid was in motion. What does any of this mean for the magnetic field? The connection is indirect but potentially significant. The magnetic field is generated in the outer core, not the inner core. But the inner core influences the outer core in several ways. Heat flowing out of the inner core drives convection in the outer core. The rotation of the inner core affects the flow patterns of the liquid metal. Changes in the inner core could propagate outward, altering the dynamics that generate the geodynamo. Some researchers have speculated that the inner core's rotation cycle might be linked to variations in the magnetic field strength. If the core's rotation affects convection in the outer core, and convection affects the magnetic field, then a 70-year cycle in core rotation might correspond to fluctuations in field strength on similar timescales. The evidence for this link is circumstantial. The magnetic field has weakened over the past century and a half, but whether this weakening is related to inner core dynamics is unknown. The timescales are suggestive but not conclusive. What is clear is that Earth's deep interior is more dynamic than anyone imagined a few decades ago. The planet is not a static ball of rock and metal. It is a churning, evolving system. Heat flows outward from the center. Metal crystallizes at one boundary and melts at another. Convection, Patterns shift over years and decades. The core rotates at its own pace, speeding up and slowing down in response to forces we're only beginning to understand. This dynamism is what makes life possible. Without the churning outer core, there would be no magnetic field. Without the magnetic field, the atmosphere would erode, the oceans would evaporate, the surface would be sterilized by radiation. The living Earth depends on a dying core. The heat that drives the geodynamo is finite. Eventually, perhaps 1 billion years from now, the core will cool enough that convection stops. The magnetic field will fail permanently. Earth will join Mars and Venus as another dead world orbiting the Sun. That fate is far in the future, but the changes happening now, the slowing of the inner core, the expansion of the South Atlantic anomaly, the racing of the magnetic pole toward Siberia, remind us that the system is not static. It operates on timescales that dwarf human civilization but include occasional punctuations, events that unfold over centuries rather than millions of years, events that our species might live to witness. The question is, what those events would mean for a world that depends on electricity, satellites, and invisible signals crisscrossing the sky. A world that has built its entire infrastructure on the assumption that certain features of the planet are stable. In the next chapter, we will examine those vulnerabilities. We will ask what a magnetic collapse would do to modern technology, and we will consider whether civilization could survive. Chapter 9. The Modern World at Risk. Imagine waking up to a world without satellites, no GPS. Your phone cannot find your location. Your car's navigation system displays a blank screen. The delivery trucks that stock grocery stores cannot optimize their routes. The tractors that plant and harvest crops on industrial farms cannot guide themselves across fields with centimeter precision. Aircraft must rely on older navigation methods, reducing the number of planes that can safely occupy the sky. No satellite communication. Remote areas lose their links to the outside world. Ships at sea cannot contact shore. Disaster relief operations in regions without ground infrastructure cannot coordinate effectively. The global network of financial transactions that depends on precisely synchronized time signals begins to fail. Trades that should be separated by milliseconds become confused. Markets malfunction. No weather satellites. Forecasters lose their eyes in the sky. Hurricane tracks become uncertain. Tornado warnings come later or not at all. Farmers cannot plan for frost. Airlines cannot route around storms. The death toll from extreme weather events rises. This is not science fiction. This is what happens when the space environment becomes hostile enough to destroy our orbital infrastructure. And a weakened magnetic field makes this scenario more likely. The Van Allen belts already pose challenges. Satellites must be designed to withstand the radiation environment of their intended orbits. Shielding adds weight. Radiation-hardened electronics cost more, but the current environment is manageable. We know the hazards, we design around them. Now imagine the magnetic field at 10% of its current strength. The Van Allen belts would still exist, but their inner edges would dip closer to Earth. Regions of space that are currently benign would become hazardous. Satellites designed for the current environment would fail earlier than expected. New satellites would need more shielding, more radiation hardening, more mass devoted to protection rather than capability. The South Atlantic anomaly would expand dramatically, perhaps covering the entire planet. Low Earth orbit would become significantly more dangerous. The International Space Station might become uninhabitable. Certainly any long-duration crewed missions would face severe radiation challenges. Solar storms would hit harder. The magnetosphere normally deflects most of the energy from coronal mass ejections. During a reversal, with the field weak and chaotic, more of that energy would reach the upper atmosphere and the surface. The aurora would be spectacular, visible worldwide. But the beauty would come with a price. Power grids would be the most vulnerable terrestrial infrastructure. When charged particles from the sun interact with Earth's magnetic field, they induce currents in long conductors. power lines, pipelines, railroad tracks. Normally, the magnetosphere absorbs most of the impact. During a severe geomagnetic storm, enough energy gets through to cause problems. The Quebec blackout of 1989 knocked out power to 6 million people for 9 hours after a coronal mass ejection triggered a cascade of transformer failures. A Carrington-scale event today, with the magnetic field at full strength, would be catastrophic. Studies estimate that a direct hit from a solar storm equivalent to the 1859 event could cause trillions of dollars in damage. Power outages lasting months rather than hours. Transformer shortages because the specialized equipment takes years to manufacture. Supply chains collapsing as transportation and communication fail. Now imagine that same event with the magnetic field at 10% strength, or 5%. The energy that reaches the surface would be multiplied. The induced currents would be stronger. The damage would be worse, much worse. Engineers are aware of these vulnerabilities. In the decades since Quebec, power companies have installed protective equipment. Capacitors, neutral blockers, systems that can disconnect portions of the grid before damage spreads. But protection is not universal. Not all utilities have invested equally. Developing countries are particularly vulnerable. A global event would stress the entire system simultaneously. Communication networks face similar risks. The ionosphere, the layer of charged particles in the upper atmosphere that allows long-distance radio communication, would be disrupted during magnetic collapse. High-frequency radio, still important for aviation and military communication, would become unreliable. GPS accuracy would degrade as ionospheric variations distort the signals from satellites. The corrections that normally compensate for ionospheric effects would become inadequate. Navigation more broadly would face challenges. Magnetic compasses would become useless, not just inaccurate, but completely unreliable. During a reversal with multiple wandering poles, a compass might point in different directions at different times. Ships and aircraft rely increasingly on GPS, but GPS is vulnerable to the same solar storms that would intensify during magnetic weakness. Backup systems based on ground-based radio beacons would help, but coverage is not universal. Aviation would be particularly affected. Airline pilots flying polar routes already receive elevated radiation doses compared to flights at lower latitudes. During magnetic collapse, these doses would increase dramatically. Airlines might need to reroute away from polar regions, adding hours to flights between North America and Asia. Crew career limits would be reached faster. Pregnant passengers would face higher risks. The economic consequences would ripple through every sector. Insurance costs would rise. Infrastructure investments would need to be redirected toward hardening critical systems. Some technologies might become uneconomic. The satellite industry, already operating on thin margins, might contract. Space exploration beyond low Earth orbit would become even more challenging. And this assumes a gradual weakening over centuries, giving society time to adapt. If the collapse happened faster, the consequences would be more severe. The paleomagnetic record suggests that reversals typically take thousands of years, but excursions can happen in centuries. The Lachon, recall, saw the field drop to 5% of normal within about 250 years. That is fast in geological terms. In human terms, it is several generations. Time to adapt, but not unlimited time. The biological consequences are harder to predict. During the Lachon, our ancestors survived. Neanderthals disappeared, but the connection to magnetic collapse is uncertain. Modern humans persisted and eventually thrived. Life is resilient. But modern humans face risks that did not exist 42,000 years ago. Increased ultraviolet radiation would raise skin cancer rates. Populations at high altitudes and near the equator would be most affected. The ozone layer would thin, though the atmosphere provides substantial protection even without the magnetic shield. The effects would be measurable, but probably not catastrophic for health. Animals that rely on magnetic navigation would be confused. Birds, sea turtles, whales, salmon. Many species use the magnetic field to orient themselves during long migrations. A chaotic field with multiple poles would disrupt these systems. Some animals would adapt, others might not. The ecological consequences are difficult to predict but could be significant. The psychological effects are also worth considering. Humans have lived under a stable magnetic field for our entire existence as a species. The aurora has always been a polar phenomenon. The compass has always pointed north. Discovering that these certainties are conditional, that the planet's protective shield can fail, would be profoundly disorienting for many people. Anxiety about magnetic collapse could join climate change, pandemics, and nuclear war in the catalogue of existential concerns that weigh on modern consciousness. Is preparation possible? In principle, yes. The same technologies that would be threatened by magnetic collapse could be hardened against it. Satellites can be built with more shielding. Power grids can be equipped with more protective devices. Navigation systems can be diversified to reduce dependence on any single technology. Underground cables can replace some overhead lines. Critical facilities can be protected with Faraday cages. The challenge is cost. Hardening infrastructure is expensive. The benefits are uncertain because no one knows when or if a severe magnetic event will occur. Decision makers face the classic problem of preparing for low-probability, high-consequence events. The temptation is always to defer action, to assume that the risk is too speculative to justify the investment, to hope that future generations will solve the problem. This is the same challenge that faces climate adaptation, pandemic preparedness, and asteroid defense. The risks are real, the timelines are uncertain, the costs of preparation are immediate while the benefits are deferred and probabilistic. The difference with magnetic collapse is that we have limited ability to prevent it. We cannot control the churning of the outer core. We cannot stabilize the geodynamo. We can only observe, predict as best we can, and adapt. The current observation systems are impressive. The swarm satellites provide unprecedented detail about the field structure and changes. Ground-based observatories around the world track local variations. Computer models simulate the dynamics of the outer core with increasing sophistication. We have never known as much about Earth's magnetic field as we know today. But prediction remains elusive. The outer core is chaotic. Small changes in initial conditions lead to large differences in outcomes. We can say that the field is weakening. We can say that the South Atlantic anomaly is growing. We cannot say whether a reversal is imminent or millennia away. In the final chapter, we will weigh the evidence. We will ask whether we are overdue for a magnetic catastrophe. We will consider what the future might hold, and we will confront the fundamental uncertainty that defines our relationship with the planet we call home. Chapter 10. Are we overdue? 780,000 years. That is how long it has been since the last complete reversal of Earth's magnetic field. The Brunhes-Matuyama event, a time when our ancestors were still Homo erectus, living in Africa and parts of Asia, wielding simple stone tools and hunting across landscapes that would be unrecognizable today. Since then, the field has held. North has remained north. South has remained south. Compasses have pointed in the same general direction for longer than modern humans have existed. Longer than any culture, any civilization, any written record. The stability seems eternal. It is not. Over the past 5 million years, the average interval between reversals has been roughly 200,000 to 300,000 years. If you take this average as a guide, the next reversal is overdue by 500,000 years. We should have experienced at least 2 or 3 reversals since Brunhes-Matuyama. We have had none. Does this mean a reversal is imminent? The honest answer is that no one knows. Geological processes do not follow schedules. The average interval between reversals is just that, an average. Some intervals have been much shorter, some much longer. The Cretaceous normal superchron saw no reversals for nearly 40 million years. The field can remain stable for periods that dwarf the entire existence of Homo sapiens. There is no evidence that being overdue makes a reversal more likely. The geodynamo does not accumulate stress that eventually releases. It is not a spring being compressed. It is a fluid system driven by convection and electromagnetic forces. Whether it reverses depends on conditions in the outer core at any given moment, not on how long it has been since the last reversal. Some researchers argue that the recent weakening of the field is a sign. The paleomagnetic record shows that reversals are preceded by periods of declining field strength. The dipole weakens, the field becomes more complex, multiple poles appear, then the flip happens. We're in a period of weakening. The field has lost roughly 9% of its strength over the past 200 years. Does this mean a reversal is beginning? Maybe. Maybe not. The field has weakened before without reversing. Excursions, those brief periods when the field drops dramatically and the poles wander, but ultimately return to their original positions, happen more frequently than full reversals. The Lachance event 42,000 years ago was an excursion. The field collapsed to 5% of normal, then recovered. We might be heading toward another excursion rather than a reversal, or we might be heading toward nothing at all. The weakening could stop tomorrow. The South Atlantic anomaly is concerning but not conclusive. It has been present for at least 2 centuries, probably longer. It has grown in recent decades, but growth does not necessarily indicate an impending reversal. Anomalies can expand and contract. Reverse flux patches can appear and disappear. The current changes might be a fluctuation in a fundamentally stable system. The movement of the magnetic North Pole is dramatic but not unprecedented. The pole has wandered before. It has accelerated before. The current dash toward Siberia is unusual in recorded history, but may be normal on geological timescales. We simply do not have records going back far enough to know. The changes in the inner core are intriguing, but their connection to the magnetic field is unclear. The geodynamo operates in the outer core, not the inner core. The inner core influences the outer core through heat transfer, and possibly through gravitational and electromagnetic coupling, but the mechanisms are not well understood. A slowing inner core might affect the magnetic field, or it might not. What we can say with confidence is that the magnetic field is not fixed, it changes. It has changed dramatically in the past. It will change dramatically in the future. Whether those changes happen in our lifetimes, in our children's lifetimes, or millions of years from now is beyond our current ability to predict. This uncertainty is uncomfortable. We want to know. We want to prepare. We want to understand the risks we face. But the Earth keeps its secrets. The outer core is 3,000 kilometers away. We cannot visit it. We cannot sample it. We can only infer its behavior from the clues it leaves at the surface and the waves we send through it. The best we can do is watch. The swarm satellites continue their orbits, measuring the field with unprecedented precision. Ground stations around the world track local variations. Scientists build ever more sophisticated models of the outer core, testing hypotheses against observations, refining their understanding year by year. If a reversal begins, we will see it coming. The decline will be gradual, at least by human standards, centuries rather than decades, perhaps millennia. The field will weaken, the poles will wander, the South Atlantic anomaly will expand, the aurora will spread toward the equator. There will be time to adapt. How much time is enough? That depends on how quickly we can harden our infrastructure, diversify our technologies, prepare our societies for a world where the magnetic shield is compromised. The clock is already ticking, whether or not a reversal is imminent. Solar storms can damage power grids today. Satellite failures can cascade through our interconnected systems today. The vulnerabilities exist. The question is whether we address them proactively or wait for disaster to force our hand. History suggests we wait. Humans are not good at preparing for low probability, high consequence events. We discount the future. We prioritize immediate concerns. We assume that problems deferred are problems solved. The magnetic field does not care about our cognitive biases. It follows the physics of churning liquid iron, the dynamics of heat transfer and electromagnetic coupling, processes that operate on their own timescales regardless of what we believe or prefer. If a reversal happens, life will persist. It has before. Multiple reversals have occurred during the existence of complex life on Earth. Mass extinctions have not consistently accompanied them. The evidence suggests that reversals are stressful but survivable. Species that can shelter from radiation, that can tolerate climate variability, that can adapt their navigation systems will get through. Whether civilization will get through is a different question. We have never experienced a reversal. We have built our entire technological infrastructure during a period of magnetic stability. We do not know how our systems would perform under stress. We have models and simulations, but we have no data from actual experience. The precautionary principle suggests we should prepare, even if the probability of a near-term reversal is low. The consequences are severe enough to justify investment in resilience. Hardening power grids protects against solar storms regardless of whether a reversal is coming. Diversifying navigation systems improves reliability regardless of magnetic conditions. The preparations we make for magnetic catastrophe serve us well for other risks too. But precaution competes with other priorities. Governments face immediate crises. Budgets are constrained. Voters care about jobs and healthcare and education, not hypothetical magnetic collapse. The political economy of preparation is challenging. Perhaps the greatest value of understanding the magnetic field is philosophical rather than practical. It reminds us that we live on a dynamic planet, that the stability we take for granted is conditional, that forces beyond our control shape the environment we inhabit. The magnetic field is a gift, a shield that has protected life for billions of years, product of processes so deep and so vast that they defy direct observation. We are passengers on a ship whose engine we cannot see, whose course we cannot steer, whose fuel will eventually run out. For now, the ship sails on. The field weakens slightly, the poles drift. The anomaly grows, but the shield holds. The aurora still dances at high latitudes. The compass still points approximately north. The satellites still orbit. The power still flows. How long this continues, no one can say. The outer core keeps its secrets. The future remains unwritten. What we know is this. The Earth is alive in ways we are only beginning to understand. Its magnetic heartbeat fluctuates. Its poles wander. Its core churns and shifts. These processes have been occurring for longer than life itself, longer than oxygen in the atmosphere, longer than continents as we know them. We are recent arrivals on this ancient planet. We have built much in a short time. We have learned much about the world beneath our feet. But we have not learned everything, and the Earth is patient. It operates on timescales that humble human ambition. The pole shift question does not have a simple answer. We are probably not facing imminent catastrophe, but we are facing a dynamic system that has surprised us before and will surprise us again. The evidence demands attention. The risks demand preparation. The uncertainty demands humility. The next time you look at a compass, consider what it represents. Not just a direction, a connection to processes 3,000 kilometers down, a visible sign of an invisible shield, a reminder that the ground beneath you is not solid but alive, churning, evolving, creating the field that makes your existence possible. The shield has held for billions of years,